Hello, Mr. Luong. My name is Marilla Trin in Period 1 AP Physics C. I'm going to start off FRQ1 by defining the vertical displacement as the variable y, which is not done for us in the given diagram. Part A has us prove that the x displacement is equivalent to 2v squared times cosine squared of theta times tangent alpha minus tangent theta all over g. I'm going to start by defining three equations. The x displacement is equivalent to v cosine theta t. The y displacement is equivalent to v sine theta t plus 1/2 gt squared, and tangent of alpha is equivalent to the y displacement over the x displacement. Altering this equation gets us x displacement times tangent alpha equals the y displacement. I have the equations written out here as follows. You want to start by equating the y displacement formulas. V sine theta t plus 1/2 gt squared is equivalent to x tan alpha. From here, you want to insert the x formula into the x in this equivalent. So it's v sine theta t plus 1/2 gt squared equals v cosine theta t tangent alpha. As follows. After this, you need to recognize that every single term in this equation has at least one t, and all of those t's are able to be canceled out, leaving a single t on the 1/2 g, on what was the 1/2 gt squared. You are left with the equation v sine theta plus 1/2 gt equals v cosine theta tangent alpha. Next, you subtract the 1/2 gt from both sides, and you subtract the v cosine theta tangent alpha from both sides, leaving v sine theta minus v cosine theta tangent alpha equals negative 1/2 gt. From here, you need to move over to the side and define that tangent theta is equivalent to sine theta over cosine theta, and therefore, using algebra, you're able to define tangent theta times cosine theta is equivalent to sine theta as follows. From here, plug in tangent theta cosine theta into the sine theta on the left. They're making v tangent theta cosine times cosine theta minus v times cosine theta times tangent alpha is equivalent to negative 1/2 gt. You have the common factor of v cosine theta in both terms, so you can pull that out, and get v cosine theta times tangent theta minus tangent alpha equals negative 1 over 2 gt. From here, it's basic algebra to isolate the t. You multiply both sides by negative 2 and divide by g, getting the equation negative 2 v cosine theta times tangent theta minus tangent alpha all over g equals t. At this point, you want to bring back the x displacement equation defined in the beginning. X equals v cosine theta t. You need to plug in the equation derived for t into the t of this equation. X equals v cosine theta times negative 2 v cosine theta times tangent theta minus tangent alpha all over g, as shown here. At this point, you can multiply the v cosine theta into the equation, getting x equals negative 2 v squared cosine squared theta times tangent theta minus tangent alpha all over g, and the equation is almost complete. You just need to distribute the negative on the outside into the numerator to change the signs of the tangent theta and tangent alpha, earning the final equation of 2v squared cosine squared theta times tangent alpha minus tangent theta over g. X displacement equals 2v squared cosine squared theta times tangent alpha minus tangent theta over g. That is part A complete. Part B is much simpler. Using the formula derived in part A, we plug in the values v equals 50, theta equals 60, and alpha equals 30. Plugging these values into the formula found in part A gains the equation of x equals 2 times 50 squared times cosine squared of 60 times tangent of 30 minus tangent of 60 all over g. G is a constant equaling 9.8. It's written down here. And plugging this into a formula, g equals negative 9.8. Actually, but plugging this all into the formula on a calculator means x is about 147.28323 meters, as shown here. Moving on to part C. You're asking us to prove that the distance of the incline is equal to 2v squared cosine theta, sine of theta minus alpha, all over g cosine squared alpha. We will start by defining the statement cosine alpha equals x over d, which is your adjacent displacement and your hypotenuse, the inclined displacement. Using algebra, we can define d as x over cosine alpha. We utilize the equation found in part A, plugging it into the x value. D then equals 2v squared times cosine squared theta times tangent alpha minus tangent theta, all over g times cosine of alpha, as shown here. You combine the denominators of this equation and the equation found in part A to get g times cosine alpha. At this point, you are able to pull out the negative from gravity, earning the equation d is equal to negative 2v squared cosine squared theta times tangent alpha minus tangent theta, all over the absolute value of g times cosine alpha. Distributing the negative inside to the tangent alpha minus tangent theta changes the signs. D then equals 2v squared cosine squared theta times tangent theta minus tangent alpha, all over the absolute value of g times cosine of alpha, defined or shown here. Next, you need to change the tangents into their tangent identity of sine over cosine. So d then becomes 2v squared times cosine squared theta times sine theta over cosine theta minus sine alpha over cosine alpha, all over the absolute value of g times cosine of alpha, shown here. The trigonometric identity of tangents are expanded into this. From here, you find the greatest common denominator of the tangent identities, which would be cosine theta times cosine alpha. You multiply this to both fractions, earning the equation d equals to 2v squared cosine squared theta times sine theta times cosine alpha minus sine theta times cosine or sine alpha times cosine theta, all over cosine theta times cosine alpha, and then that term is over g, the absolute value of g, cosine alpha. As shown here, my work intercepts over here, but ignoring that, this is the combined term for those two. At this point, you are able to cancel out one of these cosine thetas with this cosine theta and combine the denominators of the fractions, canceling out cosine theta and combining cosine alpha on the top and bottom earns the equation d equals 2v squared times cosine theta single times sine theta cosine alpha minus sine alpha cosine theta all over the absolute value of g times cosine squared theta, shown here. At this point, you are able to use your combined angle identity to simplify this term into sine of theta minus alpha, meaning d equals 2v squared cosine theta times sine of theta minus alpha all over the absolute value of g times cosine squared alpha. That is part C finished. Finally, on to part D. You are having us prove that the maximum d is equivalent to v squared over g times 1 plus sine of alpha. You need to start with the equation found in part C. 2v squared times cosine theta times sine of theta minus a, alpha, over the absolute value of g cosine squared alpha. That's the equation we found, and we will be using that. Let's define the variable, the new variable, beta, as being the difference of theta and alpha, shown here. And from here, let's also prepare the fact that alpha is equivalent to theta minus beta, as shown here. We're going to use the first proofing, the difference of theta and alpha equals beta, and plug that into our sine function from the equation derived in part C, meaning that distance is equivalent to 2v squared cosine theta times sine of beta over the absolute value of g times cosine squared alpha. Here it is. And at this point, you can pull out cosine theta and sine of beta from the fraction d equals 2v squared over the absolute value of g times cosine squared alpha times all of that times cosine theta sine beta, shown here. From here, you are able to use your product angle identity to plug in or to substitute cosine theta and sine of beta. The d equals 2 times v squared over the absolute value of g times cosine squared alpha, and cosine theta times sine of beta will equal half of sine theta plus beta minus sine of theta minus beta. Shown here. This is equivalent to this. Because the 1/2 is being multiplied to the 2v squared absolute value of g cosine squared alpha, you can cancel out the 1/2 and the 2. 1/2 times 2, of course, equals 1, and therefore will not be important to the equation. D equals v squared absolute value of g over the absolute value of g times cosine squared alpha times sine of theta plus beta minus sine of theta minus beta. Here. Using the formula or the alpha up here, theta minus beta equals alpha, we are able to plug that into this part of the equation. So d equals v squared over the absolute value of g times cosine squared alpha, all times sine times theta plus beta minus sine of alpha here. I was missing parentheses. Here. At this point, we can start defining or redefining terms, because d is at its maximum point. We can now put this sign to its maximum, because this is the largest sign in the equation. Sine, the maximum sign of anything, is of course going to be 1. So I can redefine the term as v squared over the absolute value of g times cosine squared alpha times 1 minus sine of alpha, equivalent to d maximum. Because if this is at its maximum, it's going to equal 1. At this point, we look towards the bottom. We use a Pythagorean identity to show that 1 minus sine squared is equivalent to cosine squared. So d max is equivalent to v squared over the absolute value of g times 1 minus sine squared alpha. all of that times 1 minus sine of alpha. Here. Next, you need to recognize that 1 minus sine squared of alpha is a, down in the denominator, 1 minus sine squared alpha is a difference of squares. So your d maximum would then equal v squared over the absolute value of t times 1 minus sine alpha times 1 plus sine alpha, all of that times 1 minus sine alpha here. Let me extend the fraction bar to here. And you can see that 1 minus sine alpha cancels out with 1 minus sine alpha on the numerator and denominator, meaning that your d maximum is equivalent to v squared over the absolute value of g times 1 plus sine alpha, which is the equation for part D proven. Thank you and good night.